right, guys, we're going to get started again. In the first lecture we did today, we went over the main ideas of time series, right, in general, motivating the problem, and then also how do we, because of your homework assignment, how can you adapt a GPT in its most basic form for time series data so that you can create essentially a time series GPT. Okay, so that we went over all that. Now we're going to go over, now that we understand some of the key ideas, we're going to go over the code that I'll provide for you guys with a synthetic data set. And then once we finish that, I will create the assignment right on Brightspace so that you guys can start working on that. Remember, you'll have 2 weeks to complete it, and the key thing is find a data set that's interesting to you, right, and obviously make the model predict really well, right? So that's one of the key ideas. All right, as time permits, if we finish that today, then, which we might, then we'll start the next topic in sequence mining, which is RNNs, recurrent neural networks. It's another one. I have a familiar case there. And that will actually complete the sequence on time series. So you'll be aware and you'll have a set of deep learning algorithms for that type of problem. We're not going to spend too much time on that this semester, although they are important areas. And the next topic, as you can see, gets into image processing. Our very first algorithm will be stable diffusion. And then actually then from there, lots of things related to transfer learning and so on. Okay? All right. Also, remind me, or start, I'll say this now because I'll forget, and, start thinking of your term project, right? So as far as the term project, open-ended, presentations will be the week before finals. So just form groups of 3, pick a topic related to deep learning that's got some transfer learning in it, possibly. But just ask me, anything really, right, that you find interesting or whatever, and that can be your term project. But just run it by me first. Start thinking about that, and I suggest via email or however you want to do it. Just indicate who's in your group and what is the topic that you're leaning towards. Got it? And then obviously the same idea, you need to implement whatever idea you have, train, measure performance, and all that. Got it? All right, so that's officially me assigning the term project, okay? So please start working on it. You have about 6 weeks before presentations. All right, so the sign-in sheet is going around, so please make sure to sign in as part of your participation. Yes? Good question. So we are currently on week 9. Spring break counts as a week. So 9, 10, we're back 11, so the following week, 12. Do you see that? So we're currently on 9, spring break is 10, then 11, 12. Thank you. That's your second exam. Similar to the first one. Got it? Any other questions? All right, perfect. So let's get to the code. I think it's, because you guys have taken 520, this should be pretty easy and familiar. I'm not going to cover every little detail given that we cover all those same details in 520, okay? Or you can refer back to that video or the notes, right? But I'll try to address things, but it's the same architecture. The goal was not to change the architecture. So the code can be found here, GPTs for time series. So you can click on that one. And let's click on code, time series GPT. Since this is a bit of a new lecture, I don't really have notes right now or anything like that, but I've explained how it works. I do have working code, and the code is good, I think. Simple, right? So remember, simple is better than complex, okay? So this is the code that I will discuss today. As you can see, not that long. The length is really in the transformer, and you guys understand that. I will say it ends with, like I said, something like that, right? And this is essentially what we want. You don't want a straight, you don't want to have just one straight line. What does that mean? It means it just learned like the mean of the data, right? So in this case, if you notice, we have real versus predicted. So real is the blue. So you can see essentially time series is hard to read. I will give you that. Sometimes you look at it and you're like, yeah or no. You don't quite. But you can see the pattern, right? So remember that these are essentially predictions over time, right? Versus the real values over time. So that's like silicon today, silicon tomorrow, silicon the next day. I have the real values, and then what did it predict on that day, on the next one, and the next one. So it's really discretized in that sense. We just connect to make it look more readable. But you can see, so essentially, this was the real, it predicted this. Here it's a perfect mapping. Here it went down and it went down. This one, yeah, thank you. Matches. I would argue this one is off, right, in the prediction. Here, these two seem to be mapping. It's going up. This one mapped perfectly. This one trended way up, and look at this. It trended a little bit, so there you go. Do you see that? So this is one of the ways visually that you look at, and you have to look at a lot of these, right? Obviously, if you want to measure a metric, you have to come up with some metrics, but essentially, because it's regression, we're kind of stuck in the world of R squared and MSE, and you have to derive your metrics from there, okay, and so on. So I'm just giving you the bare bones idea. I'll let you guys evaluate performance more, in however you want to extend from here. Got it? But essentially, these are going to be the metrics. All right, so let's get started. I'm going to use Colab for this one. Should be, because actually this does require a GPU. I ran this on my CPU, and it took a little bit, not too long. So obviously, if you have a very large data set or increase the architecture, it can take a bit. Okay, so a GPU probably here is recommended, especially when you have lots of data. So let's open up Colab. Initially, I'm just going to use the CPU, and then I'll rerun everything on the GPU, as it takes me a bit to explain things. All right, so let's go ahead and let's take our time. Let's add the libraries. As you can see, nothing new or mysterious here. Same libraries: Torch, TorchNN functional, NumPy for a few metrics, Matplot to plot the chart at the end, sklearn, where we're using the R square, for instance. This is, by the way, in research papers on regression, it's R square is one of the metrics used, or derived metrics from R square. Torch utils are famous data loader and tensor dataset. So nothing changes there. Let's give it a minute. The next step is going to be setting up the parameters and the data. We're going to create it synthetically, but it's kind of what I described initially, as you will see. And so obviously your data, probably best to find real data and not use synthetic data. I would recommend that as a challenge for you guys. All right, so we've got the libraries, the data for selecting a CPU or a GPU. So for now, I'm using CPU. Okay. If you notice the parameters, I have a tendency to always go back to the things that I just know by, like memorize, right? And to me, I've memorized the 2017 paper, right? Attention is all you need. So sequence length is 40, just like that paper. My features here, this represents what's coming from like the plant, right? So not 8, but 10 features. So this is where your silicon, your natural gas, your whatever hydrogen, that's those variables. Over time, the 512, as you can see, the embedding size, notice for a GPT, the same 8 heads, so that the math, remember that if you change that 512, the math changes, right? You guys remember that, right? So if I have 512 and then I have 8 heads, that comes out to 64 exactly. And that's an important metric in the GPT. So I just didn't want to change that, right? To add any layers, 4 layers, a batch size 64, okay? And the number of epochs 8. And you can play with these parameters. All right, now comes the data part. Essentially, we're going to create, as you can see here, a matrix that is 1,000 by 10. All right, we're just going to create it synthetically to make our life easy. So that means there's 1,000 time steps. Okay, and we'll just, because it's synthetic data, we can just assume whatever. Every hour the readings were taken, or every 8 hours the readings were taken, but we assume that it is consistent. And the vectors are of size 10. This is where your natural gas, silicon, everything comes in. All right, so let's just add a few things first. Okay, so we're creating these synthetically. So that, let's do 8. So we're defining that we have 1,000 samples. Okay, this is just something I found for creating synthetic data. Okay, so you guys would just have a data set anyway, right? So, but it's essentially, we're going to create a vector of X, add some noise, things like that. Okay, so that's a vector X, for instance. You can see X. So it's got 10, sorry, I keep saying 8. 10 random values for now, but they will have some kind of a distribution. All right, so because we don't want, so think about this, right? So we don't want random data in this 1,000 by 10 matrix. Do you guys see that? If it's all random data, then there's no pattern to pick up. Essentially, we inject this pattern, right? So this is a common approach to create this type of time series data with a pattern. Okay? All right, so I have an X here. We're going to have our data in this list for now, and then we'll turn it into an array, a NumPy array, but it's just a list, data. Notice over here, this is where we start creating the data. So we are going to iterate from t to 1,000, from 0 to 1,000. Okay, I already created 1x, which is this one, right? And I'm going to append it to the data as the first vector. Then after that, I take that x, and I'm going to, modify it essentially. So let's take a look here. So the way that I created x here, you see, NP random features is the same way that I'm creating it here, but multiplying it times some parameter, and then I'm adding to it this. So this is also using this as a pattern, so that some kind of pattern is embedded in all the x vectors. Do you see that? So it's like you start with a random vector of 8, but then you're adding to it the pattern, if you will. So let's look at this, for instance. Yeah, you don't have, exactly. You guys don't have to do this. This is just a common pattern I found of creating synthetic data that is for time series, but it has a little pattern that the machine learning model can pick up. Hopefully you guys would actually have time series for financial markets, the stock market, so there should be in there some kind of pattern to pick up. Do you see what I'm saying? Mm-hmm. And so if you look closely, it's a good question, right? So if you look closely here, I'm just creating random vectors here, right? But every vector then is going to get this little part that incorporates the pattern. So let's see that. So here, for instance, I do this, okay, oh, sorry, not this part. This part here, and that should just be random. And it's a vector of 8. Do you guys see that it's a vector of 8? Now in this one over here, I'm going to take x also, whatever the old x was, right? Which is like essentially like looking at the old one, right? But it's being what? What is this doing? This is a matrix multiplication. Do you guys see that? And everyone is being multiplied by that matrix. So essentially, it's a trick to add that pattern into them, both the sequence and the pattern. Does this make sense? Yeah, so I mean, some very smart people came up with this, not me. But it's a smart way of creating this. Okay, so you can see here, if I do this, what do you notice? It's still a vector of 8. Do you see that? Okay, so that's essentially the approach that people take to create synthetic time series data with a pattern in it. So now let's look at the whole thing, and I'll like the whole this whole part here. Okay, so remember I'm defining that I want 1,000 time series data points. Okay, I can create this matrix A, which I think we already printed. It was 10 by 10, and that just because we're making a matrix multiplication, right, like a dot product. So here then, where am I? Yeah, here. So I create that. That's the pattern that we're adding. To start with, I create one vector. This is times 0, x of size 8. And then I add it to my data. That becomes the first one at time t. Then at time t plus 1, right, I would take that same x, right, but matrix multiplied times that pattern matrix, and that produces a vector of 8, right? So that's like information from the past plus the pattern, and then we add to it a totally random vector of 8 to make it different, right? This iteration then becomes x. So now what do we do? In the next iteration, this gets added to the list. And now what do? We take the previous T1 to create T2, right? Now we're going to create T2. How do we do that? We take T1, matrix multiplied my pattern in A, which is the matrix that I define up here. That does a dot product, matrix multiplication. And then this is a vector of 8, and then we just add a totally random vector of 8. So as you can see, it's random data, but that has components of time series, information from the previous sample, and also some kind of common thing going on. Because we're not modifying A. If you notice, A just is always the same one. Got it? All right, so again, you guys do not have to do this. This is for me to create the synthetic data. For your homework assignment on the Time Series GPT, you need to find a data set. All right, so now I believe I can run this. Okay, so it ran fine. Got my data. Now I'm going to go ahead and just do a couple of things. Convert this to NumPy, and then we're going to convert this into Torch later. But at this point, my data set is ready. I have 1,000 samples from time 0 to time 1,000, right? And they are vectors of 8. Any questions on this idea? Perfect. All right, so now that I've done this, that's, the data. Now we can do the train test split, convert it to Torch tensors and Torch, data loaders and all that, and then we can essentially dive into the architecture of the GPT, and that should be it. So notice, very easy. I explained this in the previous lecture, right, that this is a common approach that's not intuitive, right, when dealing with time series data. So what did I do here? I grabbed I sliced the first 700 samples for training, and I'm going to hold out on samples 700 to 1,000, so the last 300 for testing. So essentially I'm doing a 70-30% split. Remember, you can't cheat, right? So the model during training cannot look at the test set. Right? If we were doing a competition, I would hold out the test set so you guys wouldn't be able to train on it. All right, so I have that. Perfect. Now, make windows. This is probably tricky or not tricky, depending on whether you remember how we did this in the GPT, right? It's exactly the same approach as the GPT, but no random initial point. Like, we're not randomly picking a word in the book and then grabbing the next 40. We're just going to go the first row and slice out 40. Second row, so we start at 0. The first window goes from 0 to 40. Next window goes from what? 1 to 41. Next window goes from 2 to 42, and so on. And that's, that's how we can do it. That gives you a lot of samples for training, if you think about it. So you can see how the GPU starts to explode there, right? Because imagine if you had 100,000 samples. 0 to 40, all the way to 100,000. So it explodes. All right, so what do we need? We're going to need the data itself and the data, which is called data. And we need the sequence length, which I believe we defined at 40. And that's just for this example. It may not always make sense to be 40. I'm sticking with the consistency of the original paper just so that you learn it. And then once you understand what 40 means, you can figure out what your 40 will be for your problem. I imagine for you guys, some of you will tweak that. All right, here's the window. Remember, all we're doing is we're grabbing, like when we would grab a sentence as input and output, but they were shifted by 1. The exact same idea here. That's going to be my X and Y. So for I in range, length of R, which is 1,000, minus sequence length, which is 40. So this is a trick you have to do. You go from 0 to 660, not from 0 to 700. Why? Because if you get to 690, you only have 10 left. So there's no way for you to grab 40. Do you see that? So you have to go you have to stop at 660, so that when you get to 660, you can still slice a window of 40. Make sense? It's one of the little tricks that you have to, deal with this kind of problem. All right, so that's it. So I go from 1 to 660, and what do? Remember that R is the data. Whoops. So essentially, we're grabbing R. Okay. You see that? So we're grabbing R. So we grab 0 to 40, correct? Do you guys see that here? Because this is I plus sequence length. So, right? So let's say 0 to 40 here. But what about here? Here we grab 1 to 41 because we're doing this plus 1 over here. This is something that actually should be very familiar to you because that's how we did the GPT. It just represents the shift by 1. All right? So as you can see, this is how we're going to store our data, and now the GPT will get this batch. That's why it's called X as input. It's going to predict something, right? And it's going to compare that something to this. Questions? Yeah, so this actually is the exact same function as before, but without the random. It actually makes it easier to understand. All right, so once we've appended all these into lists for X and Y, then we just make them into NumPy arrays again, and that's it. That's our data from our data set. All right, great. So I have my data now. This part is more mechanical, is what we always do with torch. So I'm going to invoke this. Okay, make windows. Okay, we can print the shape. Print train X. Actually, yeah. Okay, so print train X shape, train Y shape, test X shape, test Y shape. Seem familiar? Right? Exactly like it was on the GPT. 40, right? So initially it was, let's say this is the batch number, right? The number of samples that you have. It would have been 660-40 because you would have IDs right there. And every 40 is what? The word, right? So you would have IDs. The NN embedding, after it would go through that, this would be what number? The size of the embedding, 512. So you, and also the batches would have been like 64 or whatever, but so this is N batch 40, 512 in the GPT after the NN embedding. In our case, it is batch number 4010 because it's still the regression values. We're going to want this to be what? 512, right? And how do we do that? With a vector projection, okay, that we talked about that. So we're just going to project by multiplying this tensor with a weight matrix, right? We're going to take it from 10 to 512. And that's it. That's the whole trick of loading the time series data to the transformer. Got it? It's expecting N batch 40 by 512. We have N 40 by 10. One matrix multiplication where the model learns those weights, what they're going to be, and that's it. That solves the problem for us. All right. Any questions on this part, guys? Perfect. So you can see how it's starting to make sense, right? It's starting to become, pretty logical. All right. So now we have our train data. Remember also this is X train, Y train, right? So the model is learning to produce this output, and it's the same data just shifted by one. That's essentially it. All right. So now this is just converting to float, right? Fixing the float 32 problem so we don't run into this error. So all of them are going to be reset at float 32. Okay, and also they are now torch tensors, right? They were NumPy arrays before. So we are there. Okay, perfect. So again, you just have to find a data set, clean it up somehow to have the shape of, time steps, comma, whatever that vector. Remember, one requirement with the homework is don't just, because you'll find a lot of data like this, don't just use one value, vector of one, just silicon, for instance. I want it to be a multi-input, multi-output kind of a thing. So yes, sir.
Would it work? Just
Well,
a vector of one, like.
Would that work with just a value of one?
Yes.
I would think it's easier actually, but that's not what I want. I want you guys to actually do this because this approach, if anything, my instinct, right? My instinct is I don't want that one because that one, then you still have to solve this one. Whereas if you solve this one, you covered that case as well. Do you see? Yeah.
I have a data set I would like to do just for my own knowledge.
Just take that one value and add a couple more. Monday, Tuesday, Do you see what I'm saying?
Yeah.
But make it multi-input, multi-output. Yeah. And in the homework, this is how I've worked with this, and in the homework, this is how I want it. I would think it's easier, but it could be harder. I don't know, honestly. So I haven't tried that. Got it?
Yep.
Yeah. All right, great. So, so we are here. we've arrived at our data is now torch tensors, very convenient, very, great. So we are ready then to just create our data loader and everything. And notice that we're moving really fast with this, right? The next step is the architecture, training, evaluation. So if you understand if you remember the GPT and all the details of it, we're done essentially, right? So train loader function, so data loader, what do? We take our, our data, train X, train Y, and we converted a tensor data set. We set the batch size, right, to be 64. So remember, we're going to give it this whole data, and it's going to make it into batches of 64. And we shuffle, remember so shuffle. Let's set that to false. Okay, so let's go ahead and run this. Okay, got it? Questions? All right, let's keep going. Now, if you look, comes the actual GPT architecture. So if you remember, I usually, what I do is I'll start at the final construct, and then we can dig deeper into all the other ones, but I can tell you right now it's the exact same architecture. Okay, so obviously we break down the transformer, the GPT, and we covered this when we did Baby Bird, right, and we did some other ones. So head section, this is going to be your attention mechanism, and I'm not we don't want to change any of the architecture. Obviously, this could be where somebody needs to invent or discover the time series attention. You know what I mean? Like, that could be a thing, but that's why that would be research. Okay. So then we have the multi-heads, same idea. We have the feed forward, the blocks, of course. We'll come back to all this. But let's start here, because this is where you put together the whole architecture. Okay? So, and then we're going to, actually, let's start here. And we're going to add those sections as we need them. So let's kind of put that here. All right, so remember, we instantiate a model. It's going to be a time series GPT from the class that we're about to define. The device, of course, CPU, GPU. And then we also need an optimizer, so we'll just use Atom. Notice that the parameters that we're training are the model.parameters from the GPT. So we need to learn those, right? And we have some kind of learning rate for this task. Okay. All right, so I'm not going to run this because it's going to break. We need to add now the class that defines the time series GPT. And you will see this is where we can make changes. So if you guys want to make changes, you can, do research or whatever. But essentially, right, it's the same architecture that we had in the past. Time series GPT is the name. It's got our constructor, which is our init function, and it's got our forward function. Okay, same as before. We inherit the nn.module, right? We initialize it. Then we're going to specify a few things here. If you remember, we would use the NN embedding in the past for the tokens and also for the positional encoding, right? Because is position important here? Yes, right? Time 0, time 1, time 2. The cat is sleeping. And the approach is actually the same one, if you think about it, right? Because for the cat is sleeping, we had ID 1, ID 17, ID 13. But then we would say 0, 1, 2. And that's the positional encoding. So here we do the same. It doesn't matter that it's vector 8, vector of 8, vector of 8. This is still the third position, the second position, the 1 position, so it's 0, 1, 2. Therefore, our NN embedding should work fine for that. We're just encoding a matrix that is 40 by 512. Got it? We just don't, what we don't have anymore is what? The NN embedding that was size 50,000 by 512. We don't need that anymore because we don't have words. But we do have the positional encoding 40 to 512 because we do have 40 positions. They're just represented now by vectors of 8 instead of IDs. Got it? This is one of the key differences that we have to understand about this adaptation. So you can see that's there. Sequence length is 40. I believe this thing tells me it's 40. Yeah, 40. And then this one should be 512. There it is. And so I'm keeping it consistent with the paper. However, this is where this would have been NN embedding, right? Of 50,000 vocab size to 512. It is not anymore, as you probably noticed. And that's because we need to do a projection. That's the simplest, cleanest solution. But the weight matrix of that matrix multiplication is what the model needs to learn. But so this is going to be features is the size of the regression vector, which I keep saying 8, but it's actually 10, right? In the code here. Got it? So that's their natural gas, silicon, hydrogen, whatever it is. Okay? And now I have my projection plus my positional embedding. Remember, those two tensors would have same dimensions, and we would just add them in the GPT. And so why not do that here as well? Remember, for the blocks, this is where we instantiate. We use NN sequential. We've discussed how this works, right? We iterate. We have, I think, 6 layers, and every layer we create in a list a block. So we have a list of 6 blocks. Remember that when that list goes into NN sequential, the data will go through them. It'll be fully connected. Got it? That's a trick in PyTorch. Layer norm, this is just a normalization of the data. And then finally, the final projection back, right? So this in the GPT, we would have gone from 512 to what? 50,000, right? And then done some kind of a softmax. No softmax needed here because this is not a classification anymore. And we're going to project down from our final embedding that is 512 into what? 10, right? Natural gas, silicon, and so on. Remember, it does not care what those things are. It just produces 10 numbers. But we have the advantage that that vector of 10 will be compared to the real vector of 10. And because of that error, we back propagate the weights, and eventually it's obligated to create things that look like that vector of 8. Do you guys see that? That's the whole trick. All right, so if you understood that, great. That's the whole architecture of the GPT right there. We just have to look into some of these, like what is a block. Remember, the block has the heads and all that. That's just a classic 2017 paper. So now let's get started. So X will come in, right? And X will be, as this tells us, BTF. What's BTF? Batch size, 64. T, the sequence of tokens, 40. And F will be 8, the vectors of 8 over the 40 positions. Everyone with me? All right, perfect. So then notice the very first step is to take, let's say 64, 40, 8, or 10, right? So here, I'm going to project 64, 40, 10 to 64, 40, what? 512, right? And that's it. Problem solved. Oh, that's the whole magic. All right, and so now that's done essentially. I got my X. Then what do I do here? I'm just gonna, this is the same trick we did, A range, right? For the sequence, right? So tokens is 40, so this is going to give us 0, 1, 2, 3, 4, 5, all the way to 40. And then pause then goes into pause embedding, which if you remember is just this NN embedding matrix, 40 to 512. 40 to 512. right? And so now, remember that, we're here. This x is then 640, 6 comma 40 comma 512, yeah? What about this one? 64 comma 40 512. But the values of each 512, right, are different. Some are in terms of position, some are directly related to the regression values. As you can see, it's the same architecture that we used in the LLM GPT. Any questions on this, guys? All right, perfect. So if you guys remember that, that's really great. Now, here's one little trick that I'm going to tell you guys, because since we're making this homework your opportunity to do more research types of things, notice this is, how do I do this? 60 comma 40 comma 512. So that's x. It comes from, that comes from the original x, right? It's just a projection of the original x to this higher dimensional x. This one is also, this is 64, sorry. I don't know why I said 60. 64. This one, just batch size. 64 comma 40 comma 512, right? But this one is coming, it's a tensor of the exact same dimension, right? So it's like I have a Rubik's Cube and another Rubik's Cube are the same. I can add them precisely, right? In hyper Rubik's Cubes. Well, here's where hopefully you see the opportunity for research. How about you add another tensor? What's the requirement? It would need to be 64 comma 40 comma 512. But you can define this yourself. It could come from x, for instance, but another view of x. So for instance, I just did a projection because I don't know what else to do. But what if you ran, so this is a very, very simple analogy, right? So normal deep learning just takes x times the weights and produces the next layer. But we also know of another methodology called the CNN, for instance. What if CNNs are useful here? So you would take the x, but now run it through a CNN. What's the only requirement? That the output that comes out is 64 comma 40 comma 512. Do you guys see what I'm saying? So you can create other operations and just add them and keep adding that 60, 40 by 512. Make sense? Now this is obviously very, this would be you doing research and discovering that for this type of problem, this would be needed. Okay? But our basic scenario is just doing this part, obviously. We need to have the positional encoding, obviously, and this is actually how we do it. And we need to have what used to be coming from the tokens, but here we're just doing a projection from 8 to 512, so that everything fits in the architecture of our GPT. Any questions, guys? Perfect. All right. So if you understand that, then remember, once we add these two, our current tensor is 64 comma 40 comma 512. What happens now? It just goes through the 6 blocks. And then the whole thing with attention happens. They get mapped into from 512 to 64. We get 8 heads. It gets concatenated. We reconstruct 64 comma 40 comma 512. Remember all of that? I'll go over it again, but just it's the same. All right, so so now we need to define blocks. So blocks is already defined here. Is just an iteration, a list of 6 blocks, right? So the next thing we need to look at is, because we don't have the code, is what is a block, right? What's in that code? So we're ready to add that class. And that's this one, block. Right? And you can see it's the same thing. We inherit an init module. We have our init function. We have our forward function. Okay? What do? These are just normalizations. Right? So that's all it is, normalizations. So x goes in ln1, ln2, and it gets normalized. What's more interesting is what happens in SA and FF, right? So SA is now instantiating the multi-head class. And what does the multi-head class do? It takes 1 and creates the 8 heads, right? That's why it's called a multi-head. And then the FF actually was pretty straightforward, if you remember. It would take the 512, map it higher, and then map it back to 512, right? So let's look at the multi-head then, because that's what needs to be added now. And that's going to be this one. All right. So here we have our init and our forward. So we figure out the head size, right? So 512 divided by 8 heads, 64, right? We have that. Then we create a module list. Remember what this one allows us to do is a list where we have 8 parallel things, right? So remember this is where 8 things run in parallel, 8 heads, because each one has an attention. So we create a list here from 4 to 8, and we just instantiate each of those heads as being of size 64. Remember that? The exact same idea that we used before. And then there's a linear projection that is used. So you can see then we once these are initialized, then we do, because we have them here, right? We've created 8 heads in this list. So now obviously each head takes in an x as input and does all the things. So we create 4h in the 8 heads that we have, plug in x into each of those heads, right? So our vector 64 by 40 by 512 goes in there into each of these heads. The result that they should produce is of size 64. So, but it's 8 heads of size 64, right? So what do we do then? On the last dimension, we concatenate them, and we once again end up with 64 by 40 by 512. Got it? And then after that, notice just another fun projection. And this projection just goes from 512 to 512. It's just a way for the neural network to have like a feed forward layer. All right? That's it. All right? So now we probably need to define head, right? The head class. So the head class, and this is the last one actually. If you remember, what happens here, this is the attention mechanism. So as you can see, we are very close to implementing a time series GPT. What happens here? Head. Again, I have my init function and my forward function. Notice that the key queries and values, right? The K, the Q, and the V, right? What were they? We've defined this many times, right? We compare X to X in the attention, but we don't compare them directly. We actually run X, we make X times a set of weights to produce a K, and then X again times another set of weights to produce a Q. And that's what we compare. So we compare K to Q, right? But essentially we're comparing X to X. It's just they go through a set of weights first. So remember that, this was something we discussed a lot, but I'll repeat. What is NN linear, essentially? X times, what is it? Times W plus B. Remember that? That's essentially NN linear, right? So that's the whole trick. The weights matrix here is written in such a way that we receive 512, but it's going to do what? Project it to 64. Because this is NM embedding is 512. This one head size, should say it. Oh, because it's going to compute it. That's why it's not there. But it's for sure 64. Do you guys see that? Yeah? All right, perfect. So now that you understand that, and let me get rid of this because it's going to error out. So I have my KQV. Remember this whole register buffer trill, that's just like the trill of ones, right? So the look ahead mask, right? So we don't let it look into the future. So if we're at 7, it can't look at 8, 9, and 10, so that's done with the mask. It just zeroes out all those things. So we did this with this trill thing. It was a 40 by 40 mask. That's almost like a constant. All right, so now that we're here, we grab X, create, K and Q. This is the attention mechanism, right? We've had many questions on exams about this over the months, right? So K times Q, the transpose of it, it is normalized by a value here. And then that way then is run through the trill, right, the mask. And then there is a softmax. We did explain all of this in great detail in 520. Remember, it took us a while, so I can show you the notes for that, but I'll, because, it's like it was these infinities, right, and the infinities became zeros and ones, right? So it's like a math trick that you do. But so refer back to the video on this, please, because it took a while to explain it. And then once I have that matrix way, which is 40 by 40 in this context, we multiply it times, we first take X and create V, then we do the matrix multiplication of 40 by 40 times our 40 by 64, and now we end up with 40 by 64, right? So this produces then, it's the output of one of the heads, and there's 8 of them. So 64, 40, 64, we get 8 of those in the end that are run in parallel, 8 attentions. So it's like you thought of the problem 8 times in parallel, and you use the attention mechanism, and then you just concatenate them on the last dimension. Do you guys remember that? Yeah, that's the math that they use, right? And so that's it. So we are using exactly the same architecture as before, and this was my intention, right? That I didn't really want to change anything from that first embedding to the last embedding. And so by keeping the dimensions as they were, it just, avoids lots of problems. All right, so now we've looked at everything. We've got all the classes, the head, multi-head. Oh, the feed forward is the last one. So I remember, we were here. So I just did multi-head, which led into head. What was feed forward, if you remember? Feed forward, and I think I haven't added this one. If you remember, after you get the tensor from the 8 heads, you concatenate them into 64, 40, 512. And what is this for, really? If you notice, all we're doing is from 512 up to a 4 times 512. Just map it to a higher dimension, if you will. And then what do we do here? From that higher dimension back down to 512. This is in the original Transformers paper, and they just decided that this was useful. Okay, got it? So you can see that's the whole architecture, I believe, if I haven't skipped anything. So let's run this. Make sure it doesn't break. Okay, so that ran. Head runs. Multi-head. Block. Time Series GPT, the whole class. And now we're going to instantiate it. Just give it a minute. There you are. So perfect, right? So we are actually getting ready to switch over to the GPU because I want to run this a little bit faster. I've got my optimizer there, so let's look at the next step. Yeah, you can see the next step is just a training, and the training couldn't be more straightforward because this is a regression problem. Instead of cross entropy, we're using MSE. Okay, so that's the only difference. So let's go ahead and do that. And I'll have to switch to the GPU for this one. Hopefully that won't. But let's go over this code first. So for epoch and epoch, so we're doing about 8 epochs. You can play with that. Put the model in training mode. You're going to keep track of the losses. Notice, because we have our nice train loader, we can just grab XB and YB, the two things that are shifted, right? In the time series context. We load them on the device. We provide XB to the model to produce YPRED. This is the magic, right? Here is just randomly providing vectors of 64, 40, 8, but we have the real data. So we minimize to produce that. So now we take YB and PRED and calculate the MSE loss. And then, our familiar zero out the grads, loss dot backward, which takes the derivatives, and then optimizer dot step, which updates the weights. We just keep track of the loss and total loss, and then we're going to print it out essentially, so that we can view the performance. So let's here switch to the GPU because this might take a little bit. So T4 GPU. All right. So let's go ahead and run all this. Okay, good. 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 Yeah, it's fine. Okay, and now the train loop. All right, there we go. Yeah, it's much faster for sure. What do you think? So, why did it? Oh, I only did eight iterations. That's right. Okay, so yeah, this was way faster than last night. All right, so let's look at the losses, right? Started at 27, about 3, 12. These are going down, right? So you guys have worked with GPTs, and this is one thing that I'm always amazed about GPTs. The losses always nicely go down. You've trained other things, you see it go up, bounce around, things like that. Even with the Time Series GPT, which is something foreign, strange, right? Unlike the text, and yet here we are. So this is a good sign, right? Right. So this is definitely a good sign because it says some learning may have happened, perhaps. All right. So yeah. So we finished the training. So now, obviously, we want to evaluate the performance in some way. And here, guys, from this point forward, again, it might depend on your data set, okay? On your goal, if you're trying to predict Bitcoin, you're trying to predict NVIDIA stock, if you're trying to predict GDP or some kind of industrial process, the silicon, whatever it is that you end up doing, your evaluation may be a little bit different here because of what you need. But I'm just providing here a simple example of getting some metrics, okay? So test evaluation, for instance. So we would put the model in eval mode, no grad, so it doesn't update the weights. We take our test X, right, load it on the device, that becomes XB. And now we're going to predict on it, right, with the trained model. And now we have our predictions. Do you guys see that? So we have our predictions. Because we're going to evaluate this with sklearn, we're going to switch it back to NumPy. Okay? And we call it, so pred, put it back on the CPU, make it into NumPy, and then of course we had test Y, which was the real data, and we call it true. So we have pred and true. Do you guys see that? The whole part of it, or a little part of it. So test X here, I think what was it like? I can't remember. Test X dot shape. All right, so it's 260, 4010. Now let's take a look at the sizes of pred. 260, 4010. And true is shape. Do you see that? So we're just seeing, trying to measure some kind of performance. Okay. So now we can try to measure performance metrics. So this is going to be our function, MSC, right? We just measure the performance of MSC. We also measure R square, and we're going to reshape our tensors. Really, the only thing that we want to analyze is these values, correct? You guys agree that the 10 values. So we reshape the whole thing for both consistently so that we can just compare the predictions regardless. So, but here, as I said, you guys can try other approaches. Let's just take a look at what this gives us. So it should give us 260 times 40, I think. Oh, yeah, sorry. Do you guys see that? So, and we can compare these essentially. So this other one would also be 10,400, 10. Okay, you can also reshape it even further. This times 10 essentially. All right, so I just printed this. These are the metrics. I'm just going to load these functions, and I'm going to measure performance. If you know anything about R square goes up to 1, right? It's from 0 to 1, actually. Although, I will say this. Statisticians will say it only goes from 0 to 1. Computer guys will tell you that you can get negatives here, even though mathematically you shouldn't. If you get negatives, it's a bad result, for sure. Something's actually funky, wonky. So, but unfortunately for you guys in your homework, it's very likely that you will get negatives on the R square, okay? It might happen. So if you see these negative values, because I've seen them, believe me, I know how frustrating it can be, just know there's something going on with your results. If you're able to get like a 0.66 positive like this, feel lucky, because it's that means actually this is good. That's like anybody that sees this would be very interested in figuring out what's going on. Got it? But remember, I did this with a very synthetic data set so that I could get something like this. Your homework assignment, as we will define it in a second, other things. But anyway, very, very real thing. This will probably be negative because sklearn can, in fact, return negatives. There's a whole reasoning for it. I can't remember right now, but there is like an explanation for it. All right, let's go ahead and do the last part, I believe, which is actually the satisfying part, and that is to plot real and predicted. I'm not going to plot all of them, of course. So if you notice, I'm actually just plotting a few. So if you want to plot more, you would do like a loop, right? So notice, first of all, from true and pred, right? So I printed these. So they were 260, 40, 10. What I'm doing is I'm just plotting 1, 40, you know what I mean? And then not 10, but 1 of them. Is this clear, guys, or no? Do you understand what I mean? So for instance, let's say that natural gas is 3. Of the vectors of 10, natural gas is 3. So I'm going to say 3 there, and I'm just plotting natural gas. That's why I was saying in your example, maybe you have, lots of let's say you have several stocks. That actually might be a good analogy. You have 10 stocks, right? And maybe by knowing how NVIDIA is doing, you can tell, well, actually, yeah, like how OpenAI is doing, right? So, or maybe actually the other way around. By knowing how Microsoft, Google, and OpenAI are doing, you would know how NVIDIA is doing, right? Because they're the ones buying the GPUs. Something like that. So, but you only care about one variable, let's say NVIDIA. So that would be variable 3. So you would plug 3 there, and that means you're only plotting the values for NVIDIA. Got it? The other thing is, there are in fact 260 different predictions that you made. So there are in fact, like saying, 260 of these charts. So you're going to view, if here I'm just viewing 1, if you want to view maybe not all of them, but every 5 or randomly or something like that, then it's in a loop, right? And you'll have several plots. And that might be the way to go. Got it? Yeah. All right. But in this example, I'm just doing, so notice the feature ID that I selected is 0. So that's this feature ID. So that's like saying natural gas. I do want the whole sequence, so that's going to be 40. And I only plot out of the 260 the first one. All right? So 1 is going to be the real, 1 is going to be the pred, some kind of little figure, and that's it. Oh, wow. Wow. Look at that. This would be really great if you could get this in real data, right? That's good. So, yeah, and that's kind of the idea, right? So obviously this is a very academic example. From here you have to dig in, and it depends on your problem. What are you giving it? What's it predicting for you, and so on. But this is the idea. Yeah, and that's, as far as the lecture, that's it. Today my goal is to start time series, right? Or what is called sometimes sequence machine learning. And I wanted to start with the time series GPT because of your homework. Right now I've covered everything, so I can definitely assign the homework to you guys, which we'll do in a second. And then you can work on this homework assignment for the next 2 weeks. It'll be due in 2 weeks. Before I end this video, and we just do other things, are there any questions? Did it make sense on the time series GPT? Yeah, go ahead.
We are predicting for the next points, right?
Mm-hmm.
Could we get better results on the 5?
Well, let me say this. You could remember it's a GPT. You're predicting 40, but because it's a GPT, you can predict the next 260. Remember how the GPT works. It just takes some input, right? So you predict 1, you concatenate that to the input, and now it predicts the next one. And you can concatenate that one to the input, and it predicts the next one. So you can predict forever. Remember, that's how it works. Now, keep in mind, so that's great. That's like I would say, wow, the other time series RNNs can't do this all the time. The GPT is made to do that. However, the downside is every prediction you're making, you're adding noise. So, and then you're passing that noise down, and so you can expect that eventually the prediction won't be as great. Do you see what I'm saying? As far as cutting it, you can explore that for your problem. Got it? All right, any other questions, guys? All right, great. So that concludes, so I'll end this video here. This concludes the Time Series GPT. The next topic we will cover after assigning the homework is RNN. So at least I'll get started with that a little bit, even though that actually takes a bit also. So let me end this here.